In the last video, we were talking about how we need to calculate the charge because we know how to calculate everything else. So I want to go ahead and describe to you how we're thinking about this oil droplet. The oil droplet is going to be a sphere. It has some R here, okay, and it has some density. We know the density. It's 886 kilograms per meters cubed. It's basically mineral oil. It's baby oil without the scent. Okay, you can make your own baby oil if you want to, just by having mineral oil. But the way you calculate, the way we're going to calculate our mass is with this relationship that we've discussed before, and that's by knowing the density. The density is just the mass over the volume. Okay. Now the volume of a sphere, and let me just do this. This implies that the mass is just going to equal to the density times the volume. Now the volume of a sphere is this. You can always look this up. It's 4/3 pi r cubed. Okay. So we're just going to put this into this particular equation, and we'll end up with our mass equaling to 4/3 pi r cubed rho. Okay, that's going to be our mass, and we know rho, and let's just say that r is some a. The next step would be to try to calculate a. And so that's going to be probably the most difficult thing, or the most tedious thing. But let's go ahead and put this back into our equation. So now we have Q is going to equal to our mass, 4/3 pi r cubed times rho. And then remember we had our G here. It's going to be times G. And then it's going to be times the quantity of the rise velocity plus the fall velocity divided by the fall velocity times E. If we look back at this equation, you'll see that we have all of that information. So now what I want to show you is, because I'm not going to derive A. A is it's an equation that that's going to come out of fluid dynamics. Basically, we have a fluid moving, or an oil droplet moving through the atmosphere, and it's about fluids. Okay, so let's go to the PDF that's associated with this, and this is actually in the experiment. So if you guys want to look at this, you may have to refer to it at different times. This is the actual experiment, and we have our chamber there, but I want to go down. And if you look on the right here, these are our considerations. Remember we had M times G right here, and then we have K V fall. That means that this oil droplet is falling. And then you have a scenario where you actually have a voltage and on this oil droplet. The oil droplet has a negative charge, and this is positive, so the charge is going to be attracted to that plate. And the force upward is E times Q, the electric field times the charge on this object. This electric field emanates from the plates. This charge here is going to be a part of what is going to be a property of this oil droplet. And the oil droplet still has mass times gravity, and now it has a resistive force, K times the rise velocity. And so you'll see that we have equation 1, we have equation 2, we had both of those in there. We come up with equation 3 right here. We did all of this. And we have our mass times our gravity piece right here, so we can put that into this equation. And so we're coming up with the same equation. And now we need to calculate A. So you know, you have the formula for Stokes' law, and this is, I haven't really gotten too deep into this, but Stokes' law is F sub F, so this is a force, equals to 6 pi times eta. Eta is the viscosity, times A, which is the radius, times the fall velocity. So this is Stokes' law. And so we'll we can calculate and we can calculate A from this law. I will say that I didn't derive this or anything like that. So, but yes, the viscosity we've talked about viscosity. We've talked about how viscosity is about the interaction between a fluid and a surface, and how viscosity has internal forces as well as forces that are external between the surface and the fluid. And so it's going to govern how this thing flows. The good part, it says, I'm not going to get into all of that, but you guys are more than welcome to read this. Okay, you can skip the heavyweight equations. It's just a bunch of algebra. You guys can do this. If you've done the Math Excel, you can do this. It's no problem. But we're going to let me see if I can find it. For whatever reason, it doesn't seem like I have it on this side. But there's another equation that I'm going to use. These are some of the values, some of the letters that are going to be associated with Stokes' law. But let me go down here. This is the equation that I want. Equation number 12. Okay. A is going to be our radius, and then you have B. B is some constant. If I pull down here, you'll see that this constant is defined here. So they give us the information, and it's pascals times a meter. We've talked about pressure. So it's 8.2 times 10 to the negative third pascals times a meter. So, and you have viscosity, gravity, density of oil, separation distance of the oil droplet or the plates in the oil droplet viewing chamber, the charge carried by the droplet in coulombs, the fall velocity, the rise velocity, the potential difference across the plates. So if you go back down here and you look at this particular equation, we have A is equal to that constant over 2P, P is the atmospheric pressure, plus 9 times the viscosity, which is eta, times the fall velocity over 2 times rho. This is the oil density right here. And then we have G, that's just gravity. And then, of course, we have P. We have B and P again. So this is the same here. So we are going to calculate the radius first. Once we calculate the radius using Microsoft Excel, we'll be able to calculate the mass right here, because the mass is just based on the radius. We already know the oil density. We already know G, which is just gravity. Once we calculate the mass, then we can calculate the charge, because we know the mass here. We have G, and we're gonna find our fall velocity and our rise velocity and our electric field, but we're gonna find our fall velocity and our rise velocity using video physics. Okay, so hopefully all of that is pretty clear. The last thing I would like to write, I probably don't have to write it, not probably, is this equation here, A. So A is equal to the square root of B over 2P squared, and P is the atmospheric pressure, plus 9 times the viscosity, which is eta, times I think that's the rise velocity. Let me see here. Nope, that's the fall velocity. Over two times rho times G, close this, minus B over 2P. We're going to be using this, okay? In the next video, we'll start looking at the experiment, okay? I'll probably break it into 2 videos, but it might just be 1. But we're going to go ahead and start working on the experiment.